Well, if you did your assignment from the last section, you're probably more than just a little tired of taking derivatives by using the definition, the limit of the quotient, the difference quotient expression. So we're going to give you some rules that are going to streamline your work a little bit. And these were all proven by definition, but we don't have to prove each one individually. It's already been done for us. Again, we stand on the shoulders of giants to be able to see ahead. The first theorem has to do with the constant rule. And the constant rule, now think about what this is saying. A function that's a constant, y equals 5, y equals -3. That's a horizontal line. The slope of a tangent line would also be, the tangent line would also be horizontal, so the slope would be 0. So it would only make sense that if we took the derivative of a constant, and this is the notation again, the derivative with respect to x of a constant c, that we should get 0. So the derivative of a constant function is 0. It doesn't matter which constant. Derivative of pi, 0. Derivative of -99, 0. Derivative of a million is equal to 0. And this guy, along with the power rule, which is the next theorem, are going to come in plenty handy as we're going to be doing a lot of polynomials and such. The power rule says that if n is a rational number, this symbol means the rational numbers, the set of rational numbers, then the function f of x equals x to the n is differentiable, and the derivative of x to the n, let's see if I can get this straightened up, there we go, is equal to n times x to the n minus 1. It's as if the exponent comes out in front as a factor, scalar factor, and then we subtract 1 from the exponent. So for f to be differentiable at 0, n must contain a number such that x to the n minus 1 is defined on the interval containing 0. So if you start getting variables in the denominator, you get a negative exponent, then you're going to have some problem. And the power rule also works when n is 1, because when n is 1, you have x to the first power, which is just x, all right? The derivative of x to the first power would be, you bring the 1 in front, subtract 1 from the exponent, and you would get x to the 0. So 1x to the 0 is 1 times 1, which is equal to 1. So the derivative of x is just equal to 1. Now let's go ahead and run through some examples using the power rule. This first one says f of x is equal to x to the 8th power. So f prime of x, you bring the exponent out in front as a constant factor there, times x to the 8 minus 1. And 8 minus 1, of course, is 7. So this is equal to 8x to the 7th power. There's my derivative. Now notice here that when I take the derivative, I use the derivative notation. I use, in this case, f prime of x. Here, I'm going to first rewrite the fourth root of x as x to the 1/4 power, because if it's written this way, then I can use the power rule. And the derivative, now I'm going to take the derivative, so g prime of x is equal to 1/4 x to the 1/4 minus 1, which would be 1/4 x to the -3/4, or if you prefer, you could write this as 1 over 4x to the 3/4 power. Now I know that's a radical in the denominator because of the index being a 4, but we can leave it in that form. This guy here, just like this guy here, I'm going to rewrite it. I'm going to write this as x to the -5 power. And notice here my exponent is a rational number. So now h prime of x is equal to -5x to the -5 minus 1, which would be -5x to the -6, or better yet, I'll write this as -5 all over x to the 6. I try to avoid negative exponents in my answer when I can. Now it says in the next example, find the equation of the tangent line to the curve f of x equal to the graph f of x equals x to the 3rd when x is -2, when x is 0, and when x is 1. So first things first, I'm going to take f of x, which is x to the 3rd power. I'm going to find the derivative because I know I can find the slope of the tangent line using the derivative. So this is going to be f prime of x, which would be 3x to the 3 minus 1, or 2nd power. All right. Now, at x equal -2, f of negative 2 would be negative 2 to the third power, which is negative 8. So my point would be the point negative 2, negative 8. That would be my point of tangency. My slope for my tangent line would be f prime of negative 2, which would be 3 times negative 2 to the second power, which is positive 12. So the equation of the tangent line for this first one right here would be y minus a negative 8 is equal to slope times x minus a negative 2 or x plus 2. That's just in point slope form. You could write this into slope intercept form if you'd prefer. So that would be plus 24 minus 8 would be plus 16. And there's the first guy. And I would do in like manner the other two. I'll go ahead if I can squeeze in as much as I can here. So let's see, f of 0, because now I'm going to try to figure it out when x is 0. F of 0 is 0 cubed, which is 0. So my point of tangency is 0, 0. F prime of 0 is 3 times 0 squared. So that's just 0. So there's it's a horizontal line. My slope is 0. It goes through 0, 0. It's the x-axis. So my line of my tangent line would be y equals 0. Now let's see if I can sneak this last one in. For x equal 1, f of 1 is 1 cubed is 1. So I have the point of tangency is 1, 1. This is at x equal 2, at x equals 0, and at x equal negative 1 here. So f prime of 1, come over here, would be 3 times 1 squared, which is 3. So I have y minus 1 equals 3. That's my slope times x minus 1, which would give me y equals 3x, let's see, minus 3 minus 2. And those are my three equations for the tangent lines to this graph at these 3 points whose x values are given. Gotta love that power rule. Next guy up. The constant multiple rule, which is pretty much what you might expect, that if you have a constant times a function and you're taking the derivative, it's just equal to the constant times the derivative of the function itself. If f is differentiable function and c is an element of the real numbers, then c times f is also differentiable, and the derivative would be the derivative of c times f of x would be c times f prime of x. So it's as if the constant just popped out in front, then you take the derivative and you multiply through. This, along with the sum and difference rule, which is going to be coming up here in just a little bit, is going to allow us to do polynomials, but this, along with the power rule, is going to help us to be able to do monomials kind of quickly. So I have a whole bunch of derivatives here that I want to find. I'm going to first rewrite this as 7x to the negative 2. So y prime would be, now I'm going to bring this 7 times the derivative of x to the negative 2, which would be negative 2x to the negative 3. Subtract 1 from the exponent, which would be 7 times negative 2 is negative 14 all over x to the third power. I just went ahead and simplified and did 2 steps at the same time. The next guy up, I'm going to rewrite this as 3/7 x to the fourth power. So f prime of x would be 3/7 times the derivative of x to the fourth power, which is 4x to the third power. And of course, 3/7 times 4 is going to be 12/7 x to the third power. Now you may have noticed that in both of these first 2 examples, I end up multiplying the constant multiple times the exponent when I bring it out in front doing the power rule. So let's see if we can kind of combine those steps in one. First, I'm going to write this as 2x to the 1/3. So y prime, it would be 2 times the derivative of x to the 1/3. I just bring the 1/3 out in front. Times the 2 is 2/3 x. Now 1/3 minus 1, subtract 1 from that, would give me negative 2/3. Now I probably wouldn't leave it in this form because I don't like negative exponents. I would probably write this as 2 over 3x to the 2/3 power and write it that way. Oh, they just get more and more interesting here. This guy here I'm going to write as 1 over 4x to the 3/5 power. That's what the fifth root of x to the third is 3/5 power, then I'm going to write this as 1/4 x to the negative 3/5. By first rewriting it, putting it into a form where it looks more like a constant times a variable to a power, then I can use the constant multiple rule and the power rule, and I can find g prime. In this case, g prime of x, I bring the negative 3/5 times the 1/4, that would be negative 3/20, and then I subtract 1 from negative 3/5. Negative 3/5 minus 1 is like negative 3/5 minus 5/5, or negative 8/5. Don't give me decimals. Okay, don't jump to a decimal to avoid the fraction. Go ahead and write it out as a fraction. So this would be negative 8/5, and then this would be negative 3 all over 20 to the x to the 8/5. Now I know what you may be thinking. Because the numerator is bigger than the denominator on this exponent, you could rewrite this x to the 8/5 means x times x to the 3/5, but I'm just going to leave it with the rational exponent like this. Okay. Next guy up, he looks a little messy because it's not x to a power, it's 2x to a power. So let's see if we can take care of this. This would be equal to 7 all over 2x times 2x times 2x, or 8x to the 3rd power, which is 7/8 x to the negative 3 power. Now I can take the derivative. Y prime equals, I bring the negative 3 out in front, that's negative 21/8 x to the, now I subtract 1, I get negative 4, and I can write this as negative 21 all over 8x to the 4th. All right. And one more to go here. I'm going to first rewrite this as 7 times 2x to the positive 4, which is 7 times 16x to the 4th, which is 112x to the 4th. Now I can take the derivative. Y prime, I bring the 4 out in front, multiply it times the constant, that's 448 x to the 3rd power. That was easy once I rewrote it. So before you get too crazy on these, make sure they're written and simplified so that you can apply these various differentiation rules. The next guy up has to do with the sums and differences. The sum or difference of two differentiable functions is differentiable, and the sum or difference of their derivatives. So it's like the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. So the derivative with respect to x of f of x plus or minus g of x is f prime of x plus or minus g prime of x. So this makes it really easy for polynomials. I mentioned that before because polynomials are sums of monomials, and we just did a whole bunch of monomials just a couple of minutes ago. So let's see if we can try some polynomials here. Differentiate. F of x equals x to the 4th minus 6x to the 3rd minus 11. Well, according to the rule, f prime of x is going to be the derivative of this minus the derivative of this minus the derivative of this, because the derivative of a difference is the difference of the derivatives. So we just take it one term at a time. X to the 4th would be 4x to the 3rd, okay, using the power rule. And this is a minus here. Now I'm going to use the power rule again. I'm going to bring the 3 out in front times that constant, so that's going to be 18x to the 2nd. And then I'm going to use the constant, the derivative of a constant, which is 0. The derivative of minus 11 would be minus 0, which I'm not going to write down. There is my answer. Now on this guy, I would probably think of him as negative 1/4 x to the 3rd plus 8x minus 19, and then take the derivative. G prime of x, negative 1/4 times x to the 3rd. Okay, to take the derivative, you bring the 3 in front and multiply it, so that's negative 3/4 x to the, subtract 1, 2nd power, plus the derivative of 8x. Now I said a little bit ago, we went through this, that the derivative of x is 1, so the derivative of 8 times x would be 8 times the derivative of x, or 8 times 1, which would just be 8. Now again, 8x is like 8x to the 1st power, so if you use the power rule, that's 8x to the 0, and of course x to the 0 is 1. 8 times 1 is 8. And the derivative of minus 19, it's a constant, that's just 0, and there's my answer. And I would leave it just like that. Now notice here in this next example that I do not have the independent variable is x. I have the independent variable as t. It doesn't always have to be x. It's probably 90% or more of the time it is. But sometimes we use derivatives of t because sometimes we try to do application problems that involve time, and we'd like our independent variable to be t to represent time. In this example, I'm going to find p prime, and this is with respect to the variable t. So same thing, use the power rule here. This is 3t to the second. Bring the 2 out in front. This is going to be plus 12t to the first, which I don't have to put the 1 down. The derivative of minus 5/3 t, because again this is like t to the first. The example before is just minus 5/3. Then the derivative of 16 is 0, so I'm not going to put a plus 0 down. That's it. That's my answer. Now in the next example it says, does the curve y equal x to the fourth minus 2x to the second plus 2 have any horizontal tangents, and if so, where? It doesn't say what are they, it just wants to know where are they. Well, first thing I'm going to do is I'm going to take the derivative. That would be 4x to the third minus 4x to the first plus 0. And I'm going to set 4x to the third, my derivative, minus 4x. If I have a horizontal tangent, that means the slope, which would be the derivative, is equal to 0. So if I factor out a 4x, I get x squared, what would that be, minus 1 is equal to 0. So I would get 4x times x minus 1 times x plus 1 equals 0. And I would get x equals 0 and plus or minus 1. That's where I'm going to have my horizontal tangents. Now you can go ahead and plug all three of these numbers back in, but that's where they're going to be. So my horizontal tangents are at, if I take 0 and plug 0 in, I get 2, so at 0, 2. If I plug positive 1 in, I get 1 minus 2 plus 2 is 1, so I get 1, 1. And if I plug negative 1 in, I get negative 1 to the fourth is 1. Minus 2 times negative 1 squared, that's minus 2 plus 2. Yep, I get 1 again, so, and at negative 1, 1. Now, if you're having trouble kind of visualizing this, your graph is probably doing something like this. Probably doing something like this. Where it goes, it's at 1, 1, it's at 0, 2, and it's at negative 1, 1. So it probably does something kind of like this. So it has a tangent line here, it has a tangent line here, and it has a tangent line here, all of which are horizontal. All right? So I went ahead and wrote them out as ordered pairs. Now, when we're able to take the derivative of a polynomial, that's a good thing, but when we're able to take the derivative of a trig function, that's an even better thing. And they have the following theorem here that defines the derivative, or states the derivative of sine and cosine functions. And they're very similar. The derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the opposite of the sine of x, or negative sine x. So remember, the derivative of sine is positive cosine, the derivative of cosine is negative sine. Okay? So let's differentiate here. In this example, y prime, 9 times the sine of x. I just said that the derivative of the sine of x was the cosine of x, so this would be 9 times the cosine of x. That was easy. And then this one I would probably think of as 1/5 times the cosine of x. F prime of x, well, the derivative of the cosine of x is negative sine x, so I would probably write negative 1/5 sine of x. Or if you wanted to, you could write this as negative sine x over 5. I like that one a little bit better. The next one, y prime, hopefully you can see this. Well, the first part doesn't involve a trig function, it's just x squared, so that's 2x to the first, or just 2x. The derivative of the cosine of x is negative sine x, so I'm going to write minus the sine of x, and the derivative of minus 11 is 0, so this is my answer. And so you need to start remembering all these rules and all these theorems, because you're going to have them memorized for not only quizzes in my class, but for the AP test as well. All right, a little bit more. Okay. Now, it says here we can use derivatives to not only determine the slopes of tangent lines, but we can also use them to determine the rates of change of one variable with respect to another. All right, this is really key, because what is slope but a rate of change? So when we are looking for not a constant rate of change like we did back in our algebra days, but an instantaneous rate of change. Think about population growth, population rates, rate of water flow, of velocity and acceleration. Those are all the different kinds of rates that we might be interested in, and that's where the derivative comes into play. If we consider motion of an object along a straight line, and they got lots of these on AP tests. You know, you have a horizontal line or a vertical. Usually, if it's horizontal, we think of going to the right as positive velocity, going to the left as negative velocity, or if it's vertical, up is positive, down is negative. A position function, and we have a little bit of background with position functions for like a free-falling object. A position function S gives the position relative to a starting point, like the origin, of an object as a function of time. And t is mapped to s of t. Now, why they use s for position, I'm not sure of the history of that, but that's what you'll see 99% of the time. And over a period of time, the change in time, delta t, the object changes its position by delta s, which is the difference in the s values. We plug in different values for t, we find the corresponding values for s, or like our y values, our dependent variable. And the average velocity, of course, is delta y over delta t, which means instantaneous is going to involve a derivative or a limit, or actually both. So in this case, we have a ball that's dropped off of a building. I've got to get my calculator handy here. A ball is dropped off of a building 160 feet tall. Its height s at the time t is given by the position function s of t equals negative 16t squared plus 160t. S is in feet, t is in seconds. We're going to find the average velocity over the following time intervals. Now, average velocity is the change in the s over the change in the t. So in this case, our average velocity would be s of 2 minus s of 1 over 2 minus 1. So s of 2, I got to plug 2 in. So 2 squared into my function here for t. It was 4. That's negative 64 plus 160 would be 96 minus s of 1. That would be negative 16 plus 160 would be 144. All over 1, I get negative 48 over 1, or negative 48. Now, because we're looking at the velocity here, and since t or s is in feet and t is in seconds, we have feet divided by seconds. This is in feet per second. You say, well, why is it negative? Because the ball is dropping downward. We said going downward would be negative. All right. Now, let's tighten this just a little bit. Let's figure out what the average velocity is over a little bit shorter span of time here, not from 1 to 2 seconds, but from 1 to 1.5 seconds. So my average velocity is s of 1.5 minus s of 1 all over 1.5 minus 1. Well, we know what s of 1 is. It's 144. And this is going to be 0.5. So the only thing that's tricky is I have to plug 1.5 in here. So that gives me, let's see here, negative 16 times 1.5 times 1.5 is 2.25. And then I'm going to add 160. And I get 124 now. So this is going to be negative 20 over 0.5, which is like a half. So this is negative 40. It's negative 40 feet per second. You say, well, why is it not traveling as fast? It's traveling downward, but its speed is 40 feet per second. Speed is the absolute value of velocity. Here it was 48 feet per second. It's because the ball hasn't been dropped and traveling for as long. Gravity hasn't had as much of an effect on it. It's going to pick up speed as time goes on. All right, now we're really going to cut the time interval from 1 to 1.1. So my average velocity again here is going to be s of 1.1 minus s of 1 all over 1.1 minus 1. So s of 1.1, let's see, I've got to take, let me clear this out, I have to take negative 16 times 1.21, that's 1.1 squared, plus 160 is going to give me 179 No, I must have hit that wrong. It's 1.1. Yeah, no, I think I hit it right. Oh, negative 16. Criminy. All right, let's try it again. Negative 16 times 1.21 plus 160 gives me 140.64. Thank you. 140.64 minus S of 1, which is 144, and that's all over 0.1. So this is negative 3.36 divided by 0.1. That would be negative 33.6 feet per second. Right now, I did this on purpose, as you might guess, to go through all this, because I wanted to show you that as the difference in time for the average velocity, if the difference in time gets less, if our delta t gets smaller as it approaches 0, would we get to the instantaneous velocity at the instant, 1 second after, at the instant that the ball is dropped off of the building? Well, that's the idea. That's the plan, Stan. It says find the instantaneous velocity. We look at the average velocity as delta t goes to 0. This is s prime of t. So let's go back to here. S of t was negative 16t squared plus 160. This is from the previous problem. Find the object's velocity at t equals 1 second. So v of t, which is s prime of t, the derivative of position, is going to be negative 32t to the first power. And of course, the derivative of 160 is 0. So v of 1 would be negative 32 times 1, or negative 32, and this is in feet per second. Now remember the other values? Hopefully you were following along with here. Notice it went from negative 48 to negative 40 to negative 33.6 feet per second until we get to the instantaneous velocity of negative 32 feet per second. And as I mentioned before, that's the velocity. The speed of the object is the absolute value of the velocity. So if they ask you for the speed, it would be positive 32 feet per second. Now, just about got this whipped, but I want to go ahead and talk a little bit more here about a free-falling object. And of course, this is neglecting air resistance. The position of a free-falling object under the influence of gravity can be represented by the function s of t equals 1/2 gt squared plus v sub 0 t plus s sub 0. You've seen this in pre-calculus, where g is gravity, so it's either negative 32 feet per second squared or it's negative 9.8 meters per second squared, because those are the only two units that we typically deal with on a free-falling object. V sub 0 is the initial velocity, so if you just drop an object, you don't throw the object, you just drop an object, V sub 0 would be 0. And S sub 0 is the initial height or position. Typically, when they're like in the last problem, it was building 160 feet tall, so S sub 0 would have been 160. So we'll try this now. It says here that a ball is thrown straight downward, is thrown this time, not dropped, from the top of a 220-foot building with an initial velocity of 22 feet per second. What is the velocity after 3 seconds? Well, let's find the position. The position, I'm going back to this guy right here, and since I'm working with feet, I'm going to use gravity to be negative 32, so this would be 1/2 times negative 32 would be negative 16t squared. My initial velocity is 22 feet, but I'm throwing it downward, so minus 22t, and I'm doing this from a height of a 220-foot building, so plus 220. So it says here, what's the velocity after 3 seconds? Well, let's think this out here. S prime of t, which is your velocity, would be negative 32t minus 22. So at 3 seconds, S prime of 3, or V of 3, would be negative 32 times 3 minus 22. So this would be negative 96 minus 22 is negative 118. And this would be in feet per second. All right. So it's thrown downward at this velocity, and it picks up at 3 seconds because of gravity. It's now traveling, if I didn't mess up, 98. Yeah, I think I got that right there. Okay. Now, if they had thrown the ball straight upward, at 22 feet per second, then it would have been a plus 22 here instead of the minus 22. What's its velocity after falling 108 feet? Well, I don't know when it's fallen 108 feet, but I can tell you right now that if it's fallen 108 feet from its initial position of 220 feet off the ground, it is 112 feet from the ground. So the position S of t, which is negative 16t squared minus 22t plus 220, is going to have to equal 112, because that's how high up it is off the ground. That's its position. This is how much it's fallen. But remember, we started at 220 feet up. So I get negative 16. I hope I have this so that it factors. I'd hate to think I have to use the quadratic formula here. So this would be minus 108 equals 0. I am going to divide through by a negative 2, and I get 8t squared plus 11t plus 54. Oh man, all of a sudden I got this real bad feeling that this might not factor. Let's try. I got to get an odd in the middle, so let's try an 8t and a t. How about 27 and 2? Oh, once in a while. 27. No, hang on a second. That's plus. Oh, this is plus 108. Heavens to Murgatroyd, I wasn't going to get that one to work out, was I? So yeah, now it'll work out. So it's a 27 and a 2. I need the 2 here. I need the 27 here. I need this to be plus and this to be minus. So that'll give me minus 16 plus 27t. Yep, I'm going to get the 11t. So this t, this value is going to be negative, but this one is going to give me t equals 2. Now that's not my answer, because my answer didn't say when is it has it fallen 108 feet. This is when. It's saying what's its velocity. So now I have to find the velocity from here, which is negative 32t minus 22. And now I plug 2 in. V of 2 would be negative 32 times 2 minus 22. Negative 64 minus 22 is negative 86. So the velocity, all right, here I'm going to write the velocity after of the ball after 3 seconds is negative 118 feet per second. Or you could write positive 118 feet per second and then state downward. Here, the velocity of the ball, hopefully you can read this, when it has fallen 108 feet is negative 86 feet per second. All right. Now there's a lot more that we can do with these types of problems, but these applications are classic problems of stuff that you will see on the AP test. So you definitely want to practice, practice, practice.